All right, welcome ladies and gentlemen. This is video number 2 in the first half of chapter 7, a discussion about electron configurations. This video is on exceptions to electron configurations. So now that we're feeling totally awesome and rad and jazzed about being able to determine electron configuration straight from the periodic table, now I'm going to tell you that there are some exceptions to that. And really the subtitle of this video is called Transition Metals Are Weird, because they are. And those are our exceptions. And it's like, why are they weird? Because they're truly bizarre sometimes. So 4s and 3d. Really, when we talk about the exceptions to electron configuration, we're only limiting ourselves to this discussion between 4s and 3d. 4s and 3d are weird. Their energies, the energy that the 4s subshell has, the energy that the 3d subshell has, they are frighteningly similar. There really isn't that much difference between them, and we don't see the same kind of similarity between any other two sets of subshells. We don't see it between like 3d and 4p. There's a pretty big jump there. We don't see it between even 5s and 4d. It really is 4s and 3d. Their energies are frighteningly similar. So when electrons are filled in atoms, 4s will be lower in energy than 3d, which is why we fill it first, right? That's why we put electrons there first before we start putting electrons in 3d. However, 4s is only lower in energy than 3d if the 3d subshell is unfilled. Which, if you're talking about an atom and we're thinking about like filling electrons and writing electron configuration, yes, 3d will be unfilled when we get to filling 4s. So like we're good there. But as soon as electrons are in both the 3d and the 4s subshells, the energies of those subshells change. They don't change wildly, but they do in fact change, and they change enough where the tiny, a difference between them now alters, and it alters in the other direction. Meaning, 4s is lower in energy than 3d if 3d is empty. So that's why we put electrons in 4s first. But as soon as you have electrons in both 4s and 3d, now 4s actually becomes higher in energy than 3d. 3d actually becomes lower in energy. And the thing is, we might have expected this from the beginning, because you would expect that the energy level 4 has a higher energy than energy level 3, because it does, right? So it's weird that we put electrons in 4s before we put electrons in 3d. That's an exception to this rule. Like, why are you filling shell 4 before you're filling shell 3? But this rule then, it goes back to being normal as soon as you have electrons there. They're weird, man. Transition metals, they're so bizarre. So with that in mind, remember that we have an energy cost to putting 2 electrons in the same orbital because of electron-electron repulsion, right? 2 electrons in the same orbital, there is going to be an electron repulsion there. And that repulsion is essentially what's going to be contributing to this difference between 4s and 3d. The exceptions to the electron configurations are going to be seen with elements that are in period 4 in the transition metals. So expected configurations for chromium and copper. So chromium is here, copper is here. And we would expect the electron configuration for chromium to be, you know, argon, and then 4s2, 3d, 1, 2, 3, 4. And we'd expect copper to be 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. We anticipate that. However, those are not the actual electron configurations for chromium and copper. And it's due to a combination of that energy cost of putting 2 electrons in the same orbital, and the fact that the energies of 4s and 3d alter. Oh, sorry, the energy of 3d alters as soon as electrons are placed in it. So the actual configuration for chromium and copper are these. Chromium is 4s1, 3d5, and copper is 4s1, 3d10. Now, the chromium one, we're going to address to the nature of the electron-electron repulsion, because if I just look at the valence shell the outermost electrons in chromium, 4s2, 3d, sorry, this is 3d, so there's 5, 1, 2, 3, 4, right? That's what you'd expect. But this right here, remember, this is going to have some electron-electron repulsion. That is an energy cost, right? That's higher energy state, because having two negatives in the same place, they don't want to be in the same place. And as soon as we start putting electrons in this sucker, remember, the energy of this sucker changes. So what we actually see is this configuration of 4s, 1, 2, 3, 4, 5, 3d, of 4s1, 3d, 1, 2, 3, 4, 5. Now this, I think, can be very well explained by now saying there is no electron-electron repulsion. Every electron is in an orbital by itself, so you are minimizing the energy of the atom by having this particular configuration. This only happens with chromium, though. You'd expect it to happen with molybdenum, which is in the same group as chromium, and tungsten, which same thing. But no, it doesn't, because 3d is the weirdo whose energy changes, and it's so close in energy to 4s. So we'd expect chromium to be 4s2, 3d4. It isn't. It's 4s1, 3d5. Thinking about electron-electron repulsion in the orbital configuration can help explain that. Copper is the other one. You think it would be 4s2, 3d10, where you'd have 4s filled, and then 3d, just to change this into copper, would be that's 5, 6, 7, 8, 9. But having electrons in 3d actually is lowering, in this case, it's lowering the energy, in the copper's case, of the 3d subshell a little bit. So now it's going to be 4s1, 3d, and then 3d is going to be completely filled. So it is absolutely an exception to the expectations due to the weird, bizarre, transition metals, they're so weird. They do such bizarre things. Due to the weird, bizarre energy shifting as soon as the electron, as soon as you start putting electrons in 3D. Do I know why the energy of 3D changes? No. Have I done a lot of looking around online to try to figure it out? Yes. Can I find an answer? No. So I don't have a good answer for you guys. Why does this happen? Because it does. Quantum mechanics, right? That's always the go-to. Quantum mechanics. Why does it happen? Quantum mechanics. We don't know, right? But it does. We do know that. So we have some exceptions to electron configuration because of this weirdness. The other weirdness, the other takeaway from this other weirdness is transition metal ions. And this is a really big one because the AP, I've seen them ask this question on the free response like a lot, like frighteningly a lot, like every other year a lot. So this is definitely something we want to know. Ions for transition metals, especially our lovely little, 3D transition metals. Transition metal ions will hold their remaining electrons in the D sublevel because once you start putting electrons in 3D, 3D becomes lower in energy than 4s. 4s will then become the highest energy subshell. So what does that mean? This is what it means. Transition metal ions will lose their s electrons first. We should be thinking with ions, obviously you want to lose your valence electrons first. That makes sense. You're not going to pull from a lower energy level. You're going to pull from the outermost energy level. But when it comes to 4s and 3d, we will fill 4s first and then fill 3d. But when you're taking electrons away, the tables have turned. Now you're going to remove electrons from 4s first because putting electrons in 3d lowers its energy, and which means that 4s will then be higher in energy than 3d. So you take away the 4s electrons first. And this fact actually explains why so many transition metals have a +2 charge, because how many electrons can you fit in the s subshell? Oh, you can fit 2. So if they lose those 2 first, it would make sense that so many transition metals have this +2 charge. So an example of this, what I mean by this, is zinc and titanium. The zinc electron configuration for the atom is right here, 4s2 3d10. So when this becomes an ion, you are not going to touch anything in 3d10 first, right? Zinc has a +2 charge. What it means is we are going to lose these suckers. These are the electrons that are lost. The 4s electrons. We take those away, we have a +2 charge. And this right here is the electron configuration for the zinc ion. Argon 3d10. And this should make sense because now this is a complete n equals 3 energy shell, right? Energy level 3 is totally full. You don't have anything in energy level 4. For titanium, and I want to do another example that would start taking things away. So titanium to titanium 3, you obviously have to lose 3 electrons. So we're going to lose these 2 electrons. Once those 2 are gone, now we're going to start removing from 3D. So you will start removing electrons from 3D, but only after you've taken away the s electrons. So the 3 electrons that we lost were 2 of those and 1 of these guys. And the Y is just right here. Again, once both 4s and 3d have electrons, 4s becomes higher in energy than 3d, and we'll always, always, always lose our highest energy electrons first. Weird? Yes, absolutely. Absolutely, it's bizarre. But, you know, quantum mechanics, that's our reason for everything in this chapter.